Good evening, good afternoon. Yeah, good afternoon, dear student. It's not yet 6. Currently, it is 3:38, but that's not a problem. I just want to have a first session. Even if you are not currently online, you will watch the video later on. I thought this video is a crucial, this session is a crucial one because last week we couldn't have our normal session, so we missed 2 sessions. That's approximately 3 hours. So I want to try to have some sessions so that we can catch up. Okay, so this is an introductory session. And as I mentioned to one of the students, that is Samukoto, he was in my office last week. And I asked him to read about LP spaces. LP spaces is about L stand for Lebesgue spaces. LP is Lebesgue spaces, right? It's a family of space. A family of spaces, there are many. P is a real number, an integer, positive integer, because it starts from 1 to infinity, from 1 up to infinity. So that's LP. Why am I stressing on that? Because normally after your degree, that is when you have your BSc degree, in most of the university, you are supposed to have done integration theory, measure and integration theory. Of course, it's not the case all over, right? But that is the tendency worldwide. But in some countries, some universities in mathematics, they don't cover that. So, and in functional analysis, you cannot do proper functional analysis without the LP spaces. So even in the prescribed textbook, there's a chapter, which is chapter 3. It's about LP spaces. And in order to tackle the LP spaces, you need to know what is a sigma algebra. Sigma algebra, measurable functions. So those are the tools that you need to know to tackle the LP spaces. And during the first semester, for those of you who did not take stochastic processes, in that course, in that module, stochastic processes, the first part is about sigma algebra. Yeah, it's about sigma algebra and measurable functions. Because to define a probability is a measure. When you say probability, it's just a measure. So that's why we tackled measure theory. And I'm sure you know what is a random variable, because in probability you all do random variable, which is defined to be a function, right? It's a function. So it's a measurable function. So already from random variable, you already have an idea of what is a measurable function. So I've uploaded a 16-page PDF file on random variables. And actually, in that file, you get the definition of what is a sigma algebra, what is a measurable function, what is a measurable space, and the like. It's fundamental for LP spaces. So please go through that. It's just 16 pages. You can read that in, you can take 2 days maximum to read that. Just read, first of all, to just read so that the idea will get into your brain. You don't need to understand. Read the first time, and then second time, read to try to understand. So that's the advice I'm giving you. Okay. But still, in this class, I will take a few hours just to go through those concepts. Because I want you to know. Knowledge is very important. I want you to know. So that when they will talk about this or about that, you have an idea and you could have your say. Very important. So what is functional analysis? To make it short for you, to make the difference, I mean, to define what is functional analysis, you already know what's real analysis, right? I will not go too far. I will use real analysis to define what is functional analysis or what you expect to see in functional analysis. Okay, in real analysis, in general, when you say real analysis, it's just the analysis of the real line, R, the set of real numbers. You know, in real analysis, you define what is a sequence. In fact, you know already what is a sequence from set algebra and trigonometry. But the add-on here is the knowledge of what is a converging sequence. So you have a converging sequence, you have the, I don't want to use the word, but that's the word, the topology. The topology of the real line. That's real analysis. Topology of the real line. Topology meaning that you define what is an open set, what is a closed set, and you use that to define the neighborhoods of a particular point. And from the definition of the neighborhood of a particular point, you can define what is a converging sequence. Right. So that is what you do in real analysis. It's around that. And then you have the definition of is it Banach? Yeah, you don't call it Banach that way, but you call it a complete metric space. Do you even call it that way? Real analysis. Anyway, yeah, but that's what it's supposed to be. I don't know if those are the terminology that you use. You define what is a Cauchy sequence. Cauchy, we say Cauchy, it's Cauchy. So what is a Cauchy sequence? But in R, in the real analysis, a Cauchy sequence is converging with the absolute value. Absolute value in R is a metric. It's a metric. It allows you to measure the distance between 2 points. So if I want to measure the distance between x1 and x2 on the real line, I will just take the difference, absolute value. That is my definition. It's a distance, so it's a metric. So a set, if I take a set capital E, endowed with a metric, that is a function that has some definition. So that couple is what we call a metric space, right? So what you did in real analysis, in fact, absolute value of AB, absolute value of A minus B is a distance from A to B. It's a metric. So R with the absolute value is a metric space. And it is in that metric space that you define what is a converging sequence. You define what is a Cauchy sequence, and you saw that the Cauchy sequence in R converges. So it is complete. R is complete with the absolute value. So it is a complete metric space. So that same definition, because in R you are dealing with points. So real analysis is an analysis of point in R. Now function analysis, now I'm mapping real analysis to function analysis now for you to see the difference. So everything that you know from real analysis will be transported into functional analysis, by which mean now your points now become functions. Now your set, which is a subset of R, becomes a set of functions. Now you can define the distance between two functions. And you can also define what is the convergence of a sequence of functions. Now, in a functional space, you define what is a Cauchy sequence. Now, if your functional space converges for a certain metric, you will say that it is a complete metric space, which is called a Banach space in the jargon of functional analysis. So those are the analogy. Everything that will be done will just be what you saw in real analysis will be transported into an abstract set of functions. That's why it's called functional analysis. So you have real analysis, real line, they are points. Now, functional. Now, it is the analysis of set of functions. So you have real analysis, functional analysis. Real analysis, you have a set with points or R with its points. You analyze them. Now you have functional analysis, a set of function or a space of function in which you define convergence, matrix, and whatsoever. Whatever you did in real analysis, you can study the same thing and try to generalize the concept of real analysis into set of function. That is functional analysis. That is einfach. Okay, so I hope this concept will be understood. That's functional analysis. Okay, now remember I mentioned topology. You did that in real analysis. Maybe it was not called topology, but topology. Topology is a study of position, neighborhood of point, or neighborhood of topology. You know what is a closed set, like the closed ball, or what the closed interval. Yeah, in real analysis we will talk about closed interval, open interval. So a closed interval is a closed set. Open interval is an open set. So this notion will be generalized in terms of topology. So we will do that. I uploaded already the first part of functional analysis class. I mean the course materials I uploaded. So you already have the notes with you. You can just read and go through. But we'll come back to that. But what I want us to do right away is to dive directly into the definition of a sigma algebra. Because what we define on about sigma algebra will be relatively similar when we define what's a topology. And from the definition of a topology, you can see that from the course material that I uploaded. The definition of topology, you will see that you have a set. You first have a set, a non-empty set, and over that non-empty set, you define or you construct or you define a subset of the power set, meaning that a family of subset of that set. Let's say, for instance, if you take a non-empty set, capital A, if capital A is non-empty, it has elements, right? Now, we assume that it's a countable set or it is a finite set. Then you can take its element. If you have the element, the easiest way is to take a finite set, right, with a finite number of elements. Then you can construct a power set of that. Power set P calligraphic P of capital A is a set of subset of A. Meaning that if I take a subset of the power set, it will be a family of subset of capital A. Now, on that family, I can define what you call a sigma algebra, right? Among the subset, I mean, let me put it properly. If you have a power set, from that power set, you have subsets. And now, among the subset of the power set, there will be those that will satisfy some condition that we will define. And when those conditions are satisfied, we say that that subset of a power set is a sigma algebra. So simple. It's just some axioms that we need to define. And it will be the same thing for the topology. Subset of the power set, we define some property. If those properties are satisfied, we say topology. Right. Okay, now let us dive into that. Let me share the screen with you, and I'm going to write a few things. And I think I'll also share, I mean, I can even open and edit directly from a PDF file. So we will see. Okay, so let me. I can realize that I haven't opened. I have not opened. Have not opened. Okay, let me quickly do that. I can see that I did not open that. We have to go back. Okay, to make things simple, I will go straight to the definition. I'll be using chapter 6 of the, no, sorry, chapter 3 of the prescribed textbook that you can see. Okay, that's chapter 3. Okay, let me go straight to that one and define what is a sigma algebra. Sigma algebra. Good. Sigma algebra. Now I need to share. Okay, is this one up? Okay, very good. So this is the definition. Okay, this is the definition according to the prescribed textbook. This definition have been summarized, have been reduced to these two. Textbook, in some notes, you see that the definition of sigma algebra is a bit expanded. Okay, here is the complement. So A prime is in fact, A prime is the same as what you know from set algebra and trigonometry, or let me. A prime is the same as A complement, the complement of A, right? A in S. Okay, now if, so this is the original set, the non-empty set, X is our underlying set. I will call this the underlying set. Now you can see that this is our power set, Px, and then we take a subset of S, of Px, which we denote by S. So S is what we call a family or a collection of subsets of X. Now, you know, if I have a collection of subset of capital X, it means that an element of capital X is a set, it's not a point. But elements of X are points. Okay, let me make it more clear, because this is very important to understand from the very onset, so that later on when things will be written, you will not get confused. I have a software that I used to edit or to write, like a slide, to write on slides. I want to open it. I realized that it was not open. Okay, let me open it now. And then I will open. Okay, so I'm running it. It's a program. And that the file that will be open will be like a board for me, which I can write. Okay, now I will share that with you. I will share. Okay, so this is my software. It is called Zonal. Now, whatever I want to explain, I can write it here, right? I can write my explanation here. But what I would do to make things easy for me, I will open the document, the previous document. I will open it here. Okay, so before doing, I'll create a folder, functional analysis 2021, where I will save this document. Good, now I can open. It might be difficult for me to access directly. So it might not be obvious. It might not be obvious because if I go to folder, okay. If I go to folder, will I be able I don't see the link. If I were able to see the link, I would have just clicked on that. It would have taken me. Okay, maybe what I need to do here is to put it on the. But anyway, let me proceed with the explanation, otherwise it might take a few minutes to do this. Okay, let's say that our underlying set is this. So our underlying set is this one is non-empty. So we assume that X is finite, right? So we assume that the cardinality of X is finite. Let's say it's equal to n. Obviously, this one is the cardinality of X, which is also the same as the number of elements. the number of elements of X. So they are all equivalent. So this, we assume that is N, which is finite. So it's finite dimension, finite number of elements. This is just to be able to describe the element. So if you assume that the elements are x1, x2, up to xn, like this. Okay, so we know that Pn, the cardinality of the power set Px, when the set is finite, it's you have a finite set, it will be 2 to the n, right? So this is the number of elements of the power set. If the number of elements of X here is n, you can see that is n. So the power set will be 2 to the n. An example, if we take X to be 1, 2, 3. So it's easy to see that n is 3. And the number of elements of the power set of X will be 8. And you can convince yourself to see that. So I can write so I can list all the elements of Px. So Px, the elements are, you have the element with the set with no element, which is the empty set. So he has 0 element. So we have the set with 0 element. Now we can list all the set with 1 element, which are singleton. We have the singleton 1. We have the singleton 2. We have the singleton 3. Now we can write the pairs. Subset with 2 elements. So we have 1, 2. We have 1, 3. And finally, I hope the computer will not restart. Okay, that's good, because I was not checking the battery. It was already. Okay, so the last one is the pair. The pair 2, 3. So we have 3 singleton, 3 pairs, and the last one will be all the subset of X with 3 elements, which is X itself. That is 1, 2, 3. So I'd write X directly instead of listing 1, 2, 3. So this is our power set. So now let's count 1, 2, 3, 4, 5, 6, 7, 8. 8. So, and you cannot find another subset of X which is not here. So these are all the possible subsets of X. So that's a power set. So now you can see that each element here is a set. So an element of the power set is a set. It's not a point. Now, if you want to look at elements of X, they are points. You can see this is a point, this is a point, this is a point, this is a point. You can see 1 is a point, 2 is a point, 3 is a point. These are elements of R, and R elements of R are points, right? So we can see that these are points, 1, 2, 3, they are points. But the power set, which is a set of subset, means that an element within the braces here are sets, not points. You can see that 1, like this, is different from 1, the element. This is an element, this is a set. You can see that 1 is an element of the singleton. So I can write 1 element, this is a set like that. A set with 1 element, and that element is 1. So I can write that 1 is an element of the singleton 1. Or the set made of 1 point, which is 1. Right. But you cannot write 1 like this and say it's an element of the power set. This is wrong. You cannot do this. This is wrong. You cannot write that. If an element is a set, not a point, I can write 1 is an element of X. Yes, I can say that. I can say 1 is an element of X. This is correct. Like that. Now, these are subset of X, not element of X. I cannot say the empty set belongs to X. No, I cannot say the singleton 1 belongs to X. No, I can't say that. So these are the subtle, it's just subtle, and all these notions are really, you have to be very careful not to write something that does not make sense, or that may, that may make you ridicule in front of some people. So be careful of what you write. When you write something, make sure it makes sense in the context, right? Good. Okay, now, once this is understood, now if I take S in our definition, remember in the definition of the sigma algebra, even though I haven't gone in the detail. Now, if you want to define the sigma algebra, we will take S like this as a subset of the power set. It's only on such a collection of subset of X that we will define the notion of sigma algebra. You can see that S, for instance, let me give you an example of S. In this case, example 2, I can take S to be you can see that this is a subset of the power set. Why? Because its element, because remember we say A is included in B. If and only if for any element in A, for any X element of A, X is also in B. I take an element in A, I have to show that that element is also in B. Then A is a subset of B. Now, to show that this is a subset of that, each of its elements should also be element of the power set. Now, if I take the empty set, you can see the empty set is an element. If I take set X itself, it is an element of the power set. So all the elements of S are also element of the power set. So this is true. So S is a subset of the power set. It's only on such collection that I can define the notion of sigma algebra or not. Only. Okay, so this is, I can call this S1 or S, okay, let me denote it by S sub 0. Now, there are as many as, I can define as many as subset that I want. I mean, subset of the power set. I can take any possible combination there. Any possible combination I want. Right? Any possible combination. If I want, for instance, I can even take this S1, I can define this, made of the singleton 1. This is a subset of the power set. Why? Because its only element, which is the singleton 1, is in the power set, so it is a subset. Right. Right? That's for one element. I can define S2 to be the singleton 1, comma, the singleton 2, for instance. This also is a subset of the power set. There are so many of these forms that I can construct. Right. Good. But what I can say is that this is not a sigma algebra. Because if I look at the definition of the sigma algebra, it will not be satisfied. But this one is a sigma algebra. S0 is a sigma algebra. Please check that when we look at the definition of sigma algebra. Okay, now let us go back. Let us go back to the definition. I'm going to open. Okay, let me go to the next page. Okay, from the second page, page 2, I'm going to include, oh, that's what I wanted to do a while ago and I was not able to do it, but I can still do it. Let me do that. Let me do that very quickly. I will copy. Okay, what I would do, I will copy that directly into the folder. If I do that, I will be able to visualize it directly. So copy. Okay, I haven't copied. Where should I have to go? Okay, let me go into document and see if okay, zonal is there. I open that. Good. I'll paste it directly inside. Okay, functionality 22. Okay, good. Paste. Maragia. Okay, good. So now I can open it. I can open this. Okay, I can now go to open. I can, okay, see. Oh, no. Oh. Okay, let me open it. I hope you open from the second. Oh no, you will start all over. Oh no, yes. Oh no. Oh no, that's too far. Okay, it's this one. Anyway, I don't know why I'm not succeeding to. I just want it to be exactly okay. When I want to increase it, it goes zoom out. I don't know what it's doing there. Okay, page width. Great. Great. Okay. Now, okay, good. Now I will be able to write directly here without any problem. So, okay, in this definition, you can see these are the definitions. In the textbook, they just use this two. Right? They just use the two. But in the file that I sent to you, the one that I posted, the one that I posted, let me try to open it. You see that In that, there are three definitions, right? Three, 1, 2, 3. Yes, there are three definitions. There are three definitions. Okay, I don't need even to go there, but you will see it. You will see that the definition there have been expanded this way. So the first one, we just specify that the empty set. You can just write the empty set, or you can put both, because the second this one will also show that the other one will be there. So both empty set and the underlying set have to be elements of S. These two have to be there. Good. And then you have this one, which generally is written in the following form. Now, for any element A in S, so if A is in S, its complement is also in S. And finally, we can consider this last one. That a countable union of elements of S is in S. Countable union, countable. You can see that it's countable. It's not necessarily finite, but it's countable. The countable union of element of S is still in S, meaning that S is closed by countable union, right? So for any element of S where these elements are countable, they are countable, right? The union, or the countable union of A I is still in S. So this is what we call closure by countable union. When I take countable union, it remains in the set, right? It's closed by countable union. So in general, these are the three definitions that you will see, right? Okay. Why do we need this first definition? We need this first definition to ensure that the empty set is already there. Because this axiom, one, does not tell us that A is there. Sorry, that the empty set is there. It doesn't also tell us that X is there. They just say that for any element there, its complement is there. But you don't know if the empty set or the underlying set itself are both. In fact, once one is there, the other one is there by this first axiom. So now, in some textbooks, it would depend. Some might just put empty set there, or the underlying set in S. And the other element, the complement by after this first axiom, will imply that the other one will be there. So what I mean is that if we impose that the empty set is in S, after the first axiom, automatically X, which is the complement of the empty set, and that complement of the empty set, what is it? It means that you take S itself, that is the original set, the underlying set, and you subtract this set, the empty set. So it is S itself. It is also there. No, sorry, it's also in S. Yeah, this is X, sorry. This one is this is supposed to be X, the underlying set minus the empty set, which is X itself. Yeah, it's X. So this is an element of S. So it is enough to indicate one of the two, or we can just say both are there. And then for any other set that is in S, is complementary, is also automatically there. So I advise you to attend to these two axioms, this first one, because it's really fundamental. This one. And that's why you also have in the document that I uploaded. Now, when you say sigma in the terminology of sigma algebra, it comes from this. It comes from this. Because in the definition of algebra, S will be an algebra if a finite union. That is, for an algebra, these two, for an algebra will be for any AB in S, the union, that is A union B, is also in S. So if you have the first point and the second, this one in red, we say that it is an algebra. Now, when you say algebra, it says sigma algebra is an algebra in which there is closure for a countable union. So that's where the terminology sigma comes from. Yeah. If only finite union are considered, one talks about algebra, right? And that's exactly what I was talking about here. So here, if you have finite union, the definition of sigma algebra will reduce to algebra. But if you have countably many, that's countable union, then it will be a sigma algebra. And that's the remark that is written here. The letter sigma corresponds to the countable union, right? That's where the sigma comes from. So if it's not countable, it will be an algebra. Okay, so that's the definition of a sigma algebra. And an example of a sigma algebra is the power set itself, right? Now, let us look at these two definitions. If you remember, unfortunately, I cannot open the second one with this. Otherwise, I will have to run. If I run that one again, will I be able to share? Or I will have to go to the last page, which is page 91, to append an extra page and write on top. I want to avoid it. I want to avoid that. So let me write here. Let me write it here to avoid changing or toggling from one file to another new file. It will take time. You understand my point? I want to avoid that. So now an example is similar to the one that I can still erase this, right? So example one of this slide. Now, if I take x to be 1, 2, 3, if you recall, I'm taking finite set so that it will be easy to list the element. We know what is the power set. I'm not going to write it here. We have all the 8 elements of the power set. Now, I want to show that the power set, obviously, the power set is it's a sigma algebra, but I will not do that for the power set. Let me take S0. S0, which is made of these two, the empty set and X itself. This is a sigma algebra, is a sigma algebra. Why? Why is it a sigma algebra? First of all, we have already these two elements that are there. They are both there. Now, the second axiom for this definition, or this one, which corresponds to the first axiom, for any element that I would take in S0, its complement would also be in S0. So, the empty set is in S0, right? What is the complement? Is the complement of the empty set also there? The complement of the empty set is the set of elements of the underlying set, which is X, which are not in the empty set. That's why you call the complement. So that is x itself. Is x there? Yes, it is there. Okay, now let me look at the second one, which is, so it is there. Is this complement there? What is the complement of x? Complement of x is a set of elements in x that are not in x. So that's the empty set. Is the empty set there? If I look, yes, it's there. So the empty set is indeed in S0. Now, if I take the countable union, there are only two. So my countable union will be only made of, so if I take a family of element of S0, there are only two. So any arbitrary union that I would take will still be, so if I take this arbitrary or countable union, because they are finite, I mean, it's a countable set. So if I take this, where all these AIs are elements, here, I take any of them, this union will reduce to these two. And this is X. Is X there? Yes, X is in S. So you can see that these three axioms are satisfied. Therefore, S sub 0 is a sigma algebra. So you can do the same thing for the power set. The power set, it will be exactly the same. Okay, now let me define something else. If I take a subset of X, okay, let us call, this is the first one. Now, second one, if I take an arbitrary subset of this X, that is an arbitrary element of the power set, right? So if I take A, okay, I would take that to be non-empty. The subset of X, that is, A is an element of the power set of X, right? So if I take that, and then I construct a certain S something, or I can call it S, or let me call it F. So if I take this F, I say that F is made of the empty set. You see that to be wise, I need to make sure that any set, any subset of the power set that I want to construct to be a sigma algebra, I have to include these two. So I will put the two there. Of course, I will put that at the end, and then I take A and its complement, and I append X. This also is a sigma algebra. This is a sigma algebra, and you can prove it. These two are already there. For any element here, the complement will be there. And then if you take a countable union, you see that any countable union here will just reduce to an element there. So it will still be inside. So, okay, so that is it for sigma algebra. Really important. All right, because I don't want to spend too much time on this, we already know what the definition of sigma algebra. This is a proposition, right? If S is a sigma algebra, these two will be true. Okay, this is a proposition. You see that here they use what I put here in the definition. Right? So for me, I took this in the definition. Okay, so we have all this. But I'm not going to that. For me, I will not spend that much time on all these things, right? Okay, the two trivial you can see here. Example here, they say two trivial example of sigma algebra are family consisting of the space and the empty set. Exactly what I said above. And you also have the power set itself, right? These are trivials, right? You have this one and that one. And the non-trivial, which can easily be built, is this second case that I gave you. You take A, a non-empty set, subset of X, then you construct the family with 4 elements, the empty set, that subset A itself and its complement and X. If you take this, it gives you a sigma algebra that is non-trivial. But it's non-trivial, but it is a good construct. So these are two trivial. To that one, you can add this one. It's really easy to say. Great. So those are the non-trivial. Okay. Okay, there are other examples. Sigma algebra generated by a family of subsets. This also is very important. And from this one will be constructed what we call the Borel set. It comes from this. It comes from this one. Okay, let us look at the definition, that definition. Borel set is very important because in Borel set now you'll be talking about topology. Topology, anyway. Yeah, because you can see here, open closed set, that's already topology. So when you say Borel subset or the Borel sigma algebra, from that we define also the Borel sigma algebra. And from there, we will define what we call a measurable set. Okay. Okay. So let us look at the definition. Sigma algebra generated by a family of sets. Important. All right, so K is like our S, right? But it's just a family of sets. So we fix this. We take a family of set, we fix it. We fix that one, an arbitrary family of set, of set, which is subset of X. So we fix this. We fix that, K, and now we define S of K, like this, to be the smallest sigma algebra containing K. How do you write it? Okay, this is it's already written here, but we can rewrite it in another way. We can simplify it. We also write it in some set. Oh, that's that one. Okay, we can write it like this: sigma, and then we put K here. You can also write it this way. We say that this is a sigma algebra generated by K. Instead of writing SK like this, generally sigma K or SK. S for sigma and sigma. S when you say sigma is with X. When you write sigma, you start with X. Sigma. But sigma in Greek is like this. So instead of starting with S, you just write that sigma. Is simple, right? So this is written sigma K, and the easiest way to write it, you write it this way: intersection, like this, of maybe we can write S here now, or Fi or something, or intersection of things like this. And then you write here that you take this as a sigma algebra containing, or you can write below here that K is contained in F. So this is another way to write all this. It's another way to write it. So you can see that we say intersection of F, where F is a sigma algebra. You can see here, it's an intersection of sigma algebra, similarly here, where this sigma algebra contains K. It's exactly the same thing here. So you can write it, you will see in some textbooks or some document in the literature, it will be written this way. But this way is also more convenient. See, intersection of S, where S is sigma algebra containing that. So that is what we call sigma algebra generated. And in fact, it is the smallest. It's the smallest sigma algebra containing K. It's the smallest. Because you see, you take all the intersection. So if you take the intersection, this sigma K will be contained in any sigma algebra that contains K. Let me exemplify it. Let me use a Venn diagram. Look, if I do this, this is A, and this is B. A intersection B is this portion. You can see that if I take the intersection of A and B, that intersection is a subset of A and it's also a subset of B. Right. So that's why I'm saying, if I take the intersection of all these F that contain, right, we can see that this result, which is the intersection, will be in each F. So sigma K will be a subset of this F that contain, which is a sigma algebra containing K. So this will be a subset. The way this intersection is also a subset of A is also a subset of B. So that's what I'm saying. This sigma K is the smallest sigma algebra containing K, meaning that it is contained in each of these F. So if you take this the intersection of all of them, you get that. So let me write it here, or maybe it is already mentioned in a proposition. Okay, I don't see it in a proposition. Anyway, but it's a proposition. I don't see it here, but it's a proposition. So I can say here that this SK, which I denote by sigma K, is the same. So this is the same as sigma K. It's the same thing. Sigma K is exactly the same thing. Sigma K and SK is the same. So what I will add here is that sigma K, okay, here it's non-empty, right? It's non-empty since it contains this. It contains the power set, right? It is non-empty, so but it is sigma K is the smallest. Is the smallest sigma algebra containing K is the smallest. This is very important because if you want to show that something is a sigma algebra generated by, you likely use this proposition. Is the smallest containing K. So if I want to show that something is contained, that something contains the sigma algebra, I will just show that it is a sigma algebra and it contains K. Therefore, it will contain sigma K. What I mean is that from this, I can say sigma K is contained in one of these F, where this F is a sigma algebra containing K. is a sigma algebra containing K. Good. Okay, this being said, now let us define what is a Borel set. Before doing that, here it was mentioned that that sigma S contains the power set. Why is this? Is it that so? Simply because we know that Px is a sigma algebra, right? Is a sigma algebra. That is true, we know it. Does it contain K? Yes. Look at the definition here. We took K to be contained in that. So this is a sigma algebra and it contains K. Therefore, it is one of this F. Because by definition, we took the intersection of any possible sigma algebra that contains K. Is Px a sigma algebra? Yes, it's a sigma algebra. Does it contain K? Yes, it contains K. So you can see that by definition, it's well defined because Px already satisfies this condition. Sorry, I have I don't want to okay. Okay, it's fine. It's only. All right, let us look at the Borel set. A non-trivial example of a sigma algebra is furnished by the sigma algebra of so-called Borel sets generated by the family K of open sets of Rn. Rn. Okay, we can just consider n equal to 1, then that would be R, right? Okay, if I take K, if I take K to be if I take this K, I say K is equal to the family of open set of Rn or R. I say K is equal, I'll call that tau like this, is the family of OI like this, where capital I is the set of indices, and each OI is an open set in Rn. So if I take all the possible open set of Rn, I call that entire family by tau. You can see that this will be a family of subset of what? Of Rn. Subset of Rn. So each, this is an open set of, in Rn, meaning that it belongs to Rn. Because when you say open interval in R, that open interval is an element of R. What am I saying? It's a subset of R. You know that element is subset because element in the family are subset. So this O sub R is a subset of Rn. So this Rn is like our X. Rn is our underlying set X, right? So X is our Rn. So all these OI are open set of X or our Rn. But we are going to define what is an open set. That is the concept of topology. But you know already open set from real analysis. An open or closed set in real analysis is just an open interval, right? It's an open interval. Not only open interval, we can take finite intersection of open interval. If you take a finite intersection, no, what did I say? Finite intersection. If you take an infinite intersection of open set, it's an open set. And if you take a finite union of an open set, it's an open set. We are going to see that in the definition of the topology, right? It's also defined by about 3 axioms. The way we define what's a sigma algebra. In the like manner, we define a topology as a subset of the power set. That is a family or subset of the underlying set, like in this case X, that satisfies some axiom. We say that's a topology, right? So if you have such a family of open set, if you take a family of all open set of Rn, we denote it by K, right? And now if you take the sigma algebra generated by that K, it's what we call the Borel sigma algebra, and it's denoted by Brn. So B Rn, it is by definition the sigma algebra generated by K, which is the topology, the set of all open set of Rn. So that is our Borel sigma algebra. And such an element of the sigma algebra would just be called a Borel set. So an element A, element of the sigma algebra, is called a Borel set. That is it, a Borel set. Good. I'm going to give the definition of what is a measurable function. Anyway, everything that we have seen so far here and all that, these are definitions from here. This is just a construction. This is just a construction of a measurable function. But anyway, let's go to the definition. We might come to that later on. But I want to go straight to the definition, and that's what you will find in the file that I uploaded, in the last file that I uploaded on the random variable, right? If you go to the definition is just simple. Oh, okay, this is here they're talking about a measure, but I don't want to go to measures. Measurable. Oh, okay. Measurable. To define a measurable, you first need to define what is a measure. Once you define a measure, then you can talk about measurable. No, that's not true what I said. you define a measure on a measurable space. Measurable space. But now, what is a measurable space? I don't see it clearly here in the definition, but I can. Okay, a measurable space. A measurable space is just a couple. If I have a couple, I can, if I have, already we know what is a sigma algebra. Now, if I take X like this with a sigma algebra, the sigma algebra, I can call it S like this, or I can call it X with a sigma algebra. I can take another sigma algebra that is denoted by calligraphic A, or I can use calligraphic F like this. So if S is a sigma algebra defined on X, or F a sigma algebra defined on that, this couple will be called a measurable space. So measurable space or spaces if that S or this is a sigma algebra. It's exactly the same thing in probability. Remember, probability is a measure. So all the definitions are also applied to probability. When you use a okay, in probability, you will call a probability space. When you have these two, you have this, and then you add the probability, use a measure, you say it's a probability space, like a measure space. Measure space. Okay, but it's measurable, meaning that we can define a measure on it. That's what I mean. Measurable, meaning that you can measure. To say that you can measure something means that you can define a measure on it. So it's measurable. Now, what's a measure? Now, a measure is something like the function that is being defined after this. We can see this f defined from here to there, and then they do all the definition. But I'm not going to that. I will just give you the definition, and from that, you will understand. Now, if I take a mapping, let's say I have this x and I have another one there. F different from x, where x is the underlying set, right? Non-empty set. And then we have y, another, this is a non-empty set, non-empty. This also is non-empty. Then I have a mapping from x to that. Now, on x, I defined the sigma algebra S or A. Let's say that I have the sigma algebra, this measurable space. This is a measurable space, like this, right? And here, I can also say, okay, let's define another measurable space here. If it, over y, I also have another sigma algebra that I call B. Now, F will be called, or is said to be a measurable function. A measurable function. If, so I will start from here, from y. If for any element B in the sigma algebra B, like that, the pre-image of this B is in the sigma algebra A. So I take any element here, the pre-image of an element of B is an element of A. It's like you define continuity. Or maybe that's not the way you define continuity, but we'll see. When we tackle topology, you will see that continuity is exactly similar to the way we define a measurable function. We will see that in the concept of topological space. It's exactly the same thing. So f is measurable, a measurable function, from x to y if for any element in B, the pre-image of B is in A. So, to put it short, the pre-image of any measurable set of Y is a measurable set of X, right? Because a measurable set, what is a measurable set? Remember we say here measurable, when we define the Borel set, an element of, when we say Borel set is a measurable set. So an element of the sigma algebra will be called a measurable set. A in this is called, when X is a sigma algebra, is called a measurable set. Measurable set. Measurable set. So a measurable function is a function that takes a measurable set in the range and transform it into a measurable set in the domain. Measurable function takes a measurable set in the destination set or in the range, map it back into a measurable set in the domain. So simple. So that is it for a measurable function. Now, a random variable is a measurable function. Please read the note that I uploaded. You will understand. But we'll come back to that. I think we'll stop here for today. I will likely record another one tomorrow, even though tomorrow we don't have a class, just to put you on track with what we are going to do. We missed 2 sessions last week, so and you can just download the video and watch anytime. So it should not be a problem. If I don't forget, or I'm even record it anytime by tomorrow. Please bear with me. Thank you for your kind attention. I will stop here for today. God bless you and see you next time. Bye-bye. I hope you enjoy, or you will enjoy if you didn't enjoy, or if you will not enjoy it. But I enjoy it. It was not, it's not easy for the first time, but at the end of the day, you will really enjoy. Okay, goodbye.